Hey folks, this is Major Jones here to talk to you about data hazards 2. So we're going to look at a slightly more elegant way to deal with these data hazards or these read after write hazards. And that technique is called forwarding or bypassing. So let's do that. Let's go back to our sort of, example from the last lesson about how we have this data hazard here, right? Which is the result of this add instruction trying to write to register R0 on the exact same clock cycle that this store register instruction is trying to read from R0. And last lesson we said, hey, this is a read after write hazard because R0 won't take on this new value until the end of the clock cycle, by which point R0 has already been read. So STR gets the wrong value if we just sort of let these instructions go through the pipeline the way they are now. But if we look at our data path, we might say to ourselves, okay, well, it does kind of look like there's a read after write hazard, but when the add instruction is trying to write to register R0, the value that it's writing is here in the pipeline. It's, it is available to us. It's just sort of in this advanced stage. And so then the process of forwarding says, okay, well, instead of, just sort of stalling an instruction, what we might do is just sort of add a little feedback path from this signal here to the other places in our pipeline where we might want to use that value. So you can see here, from the example above, right? If the add instruction is writing to R0, that value is present right here in the write register stage. And if store register is here in this read register stage, right, that would mean it's right over here. Then I can sort of resolve this read after write hazard, not necessarily by stalling the pipeline, but by just sort of taking this value, sending it backwards into the read register stage. And if I can detect this stuff, I can put a little multiplexer here on the, this data line that says, oh, if everything's normal, then you'll just sort of select the value that's coming out of the register. But if there's this data hazard, if there's this read after write hazard, that we can resolve by sending the value backwards from one end of our pipeline to the other, then the multiplexer can sort of select the signal that's available in this stage, and in that way sort of bypass the the portion of the read register here that would get the incorrect value otherwise. We'll come back to this picture in just a sec, but here's kind of what this looks like, right? I can take my signal here in purple. You can see it sort of going back and kind of dropping into each stage of my pipeline, and the store register, if it were here in this stage, it wouldn't take the incorrect value coming out of the register file if it was detected. It would take instead the value on this data line here, which is the correct value for R0. Okay, so I basically, in order to do this properly, I have a value, here in my write register stage, which is potentially useful here in the read register stage. By the same sort of logic, this is a value that I might need, in basically every in between stage, right? So you can imagine, if the store register instruction were also in in my evaluate address phase, in my fetch operands phase, or even in my execute phase, then in any one of these four stages, it's going to get the wrong value, since it's going to get the wrong value if I don't do any sort of stalling or bypassing, because the add instruction won't have updated register 0 until after store register has taken the incorrect value out of the register file. So I forward back to each of these stages potentially. I can let the store register instruction read from the register file in this phase, and let's say we're sort of like right behind the add instruction. So by the time the add instruction is here writing a value, my store register is here. It's trying to put a value into memory. Well, that works just fine because I can just sort of send this value back one stage and let and get the correct value for my pipeline here. If we, let's see, the only other sort of bypass or forwarding path we need to consider is here in red, specifically for kind of this combination of instructions. If I'm storing a value into memory, and then I'm also loading from that memory space or from that memory value indirectly. In that case, then what I might have is this store instruction here in this execute stage in the pipeline trying to write a value. which is in the same instance of time trying to be fetched out of the fetch operands phase, right? If the load indirect instruction is here, it's trying to read from the very data address that's being stored to here in this stage. So in order to sort of get around that, what I would do is forward or bypass the value that I'm writing here, the value that I'm trying to put into memory at, in this example, val, and sort of forward that to this spot here where I'm sort of going to skip over my memory, so that on the next clock cycle, load indirect gets the correct value for the address, gets the correct value for val. And so basically, if I do an analysis of this pipeline, this covers almost every single one of my my needs to resolve read after write hazards. There is one exception to that, which is down here in our, we'll sort of see an updated version of our data lock unit. And it has to do with the fact that, let's see, if I have a base register in my evaluate address stage, so if I'm doing an evaluate address and the base register here corresponds to the value being written in one of the forward stages, one of these two stages, then I have a bit of a problem, because I can't necessarily let the base register move forward. It's potentially being added to some sort of offset, and I need this piece of hardware, I need the adder in order to resolve that. So then in that case, whatever instruction uses that base register has to sort of wait here until the value that's writing to the destination register gets to the right register stage, at which point I can use this forwarding or this feedback path to get the correct value in my base register. But it's sort of by virtue of the fact that I need this hardware, I can't let this instruction move forward to this hardware that I still have. That's sort of the one read after write hazard that I still have to contend with. But basically in every other case, if I have when I would normally have a read after write hazard in my pipeline, I can use forwarding to resolve it. And so this is clearly much simpler logic for our data lock unit than in the previous lesson. So that's kind of nice. The one thing we have to add now is what's called a bypassing or a forwarding unit. So this gets a whole bunch of values from each of the stage registers to sort of figure out which instruction is where, and then it controls these purple multiplexers and this red multiplexer to make sure that each stage sort of gets the correct value, accounting for forwarding. And a not elegant but kind of simple way to show the logic for that is to just basically say, okay, if any of the middle stages are trying to read a source register that is the same one which is being written here on the right register stage, or that's my purple path, or if the address I'm trying to write to in my execute stage is the same as the address I'm trying to read from in my fetch operands stage, then bypass, which is to say, then change the multiplexer value so that it selects either the purple or the red path instead of sort of the normal value. I said this is kind of inelegant because there are some inefficiencies. One example is, let's say I in kind of a weird scenario that I am I have instructions in these last four stages of my pipeline that are all writing to the same register, which is being read from here. In that case, this logic would say, okay, forward to this stage the value that's being written, and the pipeline would do that, and then all the instructions would advance to the next stage, and I would have another instruction here that was trying to write to the register which this instruction is using here, and the pipeline would forward the new value again, so on and so forth. So in that case, right, if this logic were a little more elegant, then we would sort of like wait till kind of the last possible moment. But that's a little too complicated to show in this this diagram. But essentially what this does is eliminate a vast majority of our read after write hazards at the expense of some additional logic that may or may not slow down our pipeline, and some additional sort of complexity in terms of where these operands come from. All right, folks, that's all I got. I'll see you next time.